finish polar coordinates, and I need to rework the last thing we were doing here, which was an area in polar coordinates, a region of this form theta equals alpha, theta equals beta, two rays with considering angles theta between alpha and beta. Its beta is less than or equal to alpha plus 2 pi. And then inside a curve like this, r given as a function of theta. This kind of a polar region, if we want to find the area A, do what we started to write last time, and increment this in theta. Call this angle theta 0 equal alpha, and this can be theta 1 and an increment of delta theta 1. This can be theta 2 with an increment of delta theta 2, dot, 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 and the last increment is delta theta n. Between theta n minus 1 and theta n, which is equal to beta. Then what we can do is we can estimate the area in here by taking any radius at any angle within this interval. Like maybe we'll go at this angle, call this angle theta 1 star. That can be the angle in the first interval that we use to get the radius of a sector. So then what's the area of each sector? And let's say in the second sector, maybe we use this angle, call that theta 2 star. And we take the radius of a sector, a piece of pizza, like a slice out of a circle. At theta 2 star, we'll take the radius here. And so this one has radius r of theta 1 star. That'll be the first one. And this one has radius r of theta 2 star, and so on and so forth. All the way down, we estimate the area of the circle by making a bunch of sectors of circles. And this one, and an angle theta n star. We take a radius r of theta n star, and the angle theta n star, in the nth interval. And so the area of the kth sector, which has constant radius, r of theta k star in the kth sector. And we're adding up all these sector areas to estimate the area A inside this region. And then we have some increment here, the angle delta theta k. We know from geometry that the area AK of this k sector is equal to 1/2 r squared. Well, the radius is r of theta k star. Times the angle subtended. That's from our area in geometry, where if you take an angle P and a radius r, the area here, 1/2 r squared P. So we just apply that to this sector here, a piece of a circle. The area it encloses from a central angle. We said it's similar to 1/2 r squared phi, where phi is the increment here, delta theta k, and the radius is the radius out to the curve here at some point in the interval. Now we'll say that the area enclosed here is approximately the sum k equals 1. I'll write approximately for now, but I'm going to change this. sum k equals 1 to n of AK, right? We took all these sectors of circles and used them to estimate slices of pie that add up their areas to estimate the area inside this curve. Well, that sum k equals 1 to n of this 1/2 r of theta k star delta theta squared delta theta k and space. And that gives us an estimate for the area. Now what you can do is if also r of theta is continuous, then it turns out, should you take the limit of these, as the number of sectors goes to infinity, with the assumption that the width of the widest one has to go to 0, it doesn't matter how you pick these points theta 1 or theta k star. Any point in each interval, in interval 1, theta 1 star can be any angle, and interval 2, theta 2 star can be any angle. And you can break up the partition any way you like. You use equally spaced angles, or in each angle double the next one, or whatever. Just so the width of the widest one goes to 0, the number of them goes to infinity. If r is continuous, this turns out to give the same number, so that no matter what, which means you could use circumscribed sectors. You could use the maximum radius on each one and overestimate the area in each region, and you get a certain number. You could use inscribed sectors. Use this radius and this radius, the smallest radius in each region, and underestimate the actual area. Right? You could be adding up these. Take the smallest radius, right, and underestimate the area of each thing. And if you took the limit of those, you'd get the same number. And so it makes sense to say, well, the area in there must be equal to the limit of the sum because it gives us the same number. Furthermore, you can show that you can actually add up the rectangles and get the same number. Well, because of that, if we have this situation, we define the area in here to be this limit of the sum of the areas of the k sectors, partitioned any way you like with any intermediate points you like, is also this. But what is this? Yeah, it's an integral, the limit of the sum. Remember this one, calculus 1, the definite integral from a to b f of x dx. This was defined, means limit as n goes to infinity with the width of the widest one going to 0. Sum k equals 1 to n f of xk star delta xk, where delta xk was the width of the kth interval, and this was the function at any point in the kth interval. That's its definition. So this is actually, by definition, the definite integral of this. Whatever function is in here, a function of variable at an intermediate point, times increments of things, all summed to take the limit, by definition, is actually the definite integral. So this is the definite integral to the beginning angle alpha to the ending angle theta of this integrand, 1/2 r of theta, right? Just like f of xk star becomes f of x in the notation. Delta xk becomes dx in the notation. This notation then means that. So we rewrite this as 1/2 r of theta squared. Delta theta k is rewritten d theta. And we say the area is defined to be that integral. So for these kinds of areas, we have this definition, if you will, but motivated by the fact that you get the same area whether you inscribe or circumscribe, and the limit, they all become the same. Hence, A is then equal to 1/2, you can pull the 1/2 out of here, integral from alpha to beta of r of theta squared d theta is the area formula for that type of region. We'll say a region like this has area given by this construction. Hence, we've defined by that construction the area to be 1/2 integral r squared d theta. Now we want to do a couple examples of that. There's a lot of neat examples in polar coordinates, but this gives you area of a region inside a curve r of theta in polar coordinates. Then before we could just do rectangular coordinates under a curve y equals f of x. Now we can do a region of this form between two angles and with an outer curve like that. And actually it turns out this also works if r is negative, because if r is negative, then r squared is positive, and you wind up actually getting the positive area also. If it switches signs, then you have to be a little careful. But anyway, so you can do r positive or negative on the interval and it works. All right, so area in polar coordinates for that kind of region given by this integration formula. Now here's the first example. There's a bunch of really neat examples here. Find the area in the inner loop of the limicon of the loop r equals 1 minus 2 cosine theta. How about that? What does that mean? You have to draw it to see. What you do is this. You say, I remember how these work. This is an a plus or minus b cosine theta. If b is bigger than a, it's a limicon of the loop. You have to think, what is the largest radius I can get? The largest radius I can get is when cosine is -1. Then I get r equals 3. So largest radius at theta equals pi. Then I got r equals 1 minus 2 times -1 is 3. Which means that this is something I go around the angle theta equals pi. I go out 3 units, 1, 2, 3. And this is the big side of the limicon. Because it's a limicon of the loop, it comes around like this. If I mark my angle. It's a little loop. And there it is. There's about what it looks like. Now you can add some additional understanding to this by plotting some more points. Like you might want to know what's the radius here. It turned out to plot it is right here. Excellent. You might also look at the smallest radius, which is the opposite direction always. Smallest radius is when cosine equals 1. Then you get 1 minus 2 times 1 is -1. When theta equals 0. Theta equals 0, you get 1 minus 2 times 1 is -1. That's the smallest radius, the most negative. So if I turn around to 0 degrees, then I back up 1 unit and I plot this point. So I've got it drawn just right there. And then there's a couple of other important things going on here. I wonder what this angle is. How do I find this angle right here? And this angle right here, how would those be important? The reason they're important is that I'm asked to find this area. That's why I'm being asked for. How do I find that area? I write it as a simple polar region. I should mark on here too. This is important for this problem. Works for r of theta non-negative or for r of theta positive. Here, what we're looking at in this loop is running around the limits on this inner loop is actually when r is negative. What happens is if you start with theta equals pi, you get r equals 3, and you're going in this direction, that pi direction, 3 units out. Then you turn around to here, to this angle, and r is 0. And then as you turn through these angles, r is negative. You march at this angle backwards to here, at this angle, at angle 0, we said back to -1, back 1 unit this direction. Out here, we march it backwards here, and finally, at this angle, r gets back to 0. So these two angles are found by setting r equals 0. See what fun these are? They're tricky. If you put r equals 0, then you get 0 equals 1 minus 2 cosine theta, which equivalently is cosine theta equals a half. How to solve that one in the unit circle? Any point on the unit circle has coordinates cosine theta, sine theta. And so if I want, and so cosine theta is the x coordinate on the unit circle. If I want cosine theta equals a half, that's saying the x coordinate on the unit circle has to be a half. The way you do this stuff in trigonometry is looking forward to this. So this is a unit circle. This must be a half halfway across. And I'll make this line x equals a half of all x coordinates equal a half. And we observe there's only 2 points on the unit circle where the x coordinate is a half. Hence, only 2 terminal rays that can make the cosine equal a half. And only 2 angles between 0 and 2 pi that make it equal a half. What are they? Well, we notice this side down here must be a half because we went from x equals 0 to x equals a half. This side is 1 because it's unit circle. This is 1 since it's unit circle. In this triangle, the side 1/2, 1, the Pythagorean theorem forces this side to be square root 3 over 2 if you compute it. Or maybe you recognize that this is a half, this is 1, this has to be square root 3 over 2. This is the famous 30, 60, 90 triangle. Same thing here. This side is square root 3 over 2. Either way, the x coordinate is 1/2. And those are the only 2 angles between 0 and 2 pi that work. Then you can add 2 pi to either one. So how do we get this inner loop? We could do it this way. We could start, let's say, at this angle here, which evidently this is an angle pi over 3 in the triangle. So the angle clockwise must be minus pi over 3. The angle this way must be plus pi over 3. Now we can sweep out the inner loop by letting theta. Theta has to run from a smaller value to a bigger value, less than or equal to 2 pi plus the first one. So we can't start at pi and go to here. That would run us around actually the outer loop. Instead, what we start is here at minus pi over 3 and run plus pi over 3. So we observe that the area is therefore integral from minus pi over 3 to plus pi over 3, 1/2 r of theta, well, put the 1/2 outside, that's easier. 1/2 integral r of theta squared d theta. That's going to be the area of the inner loop there, where r of theta is this function here. Anybody got any questions on that? It's kind of tricky. All right, now this is equal to 1/2 the integral from minus pi over 3 to pi over 3 of 1 minus 2 cosine theta squared d theta, r theta squared. And we just have to be able to evaluate that. We talked about a problem like this last time. This is 1/2 the integral from minus pi over 3 to pi over 3. 1 minus 4 cosine theta plus 4 cosine squared theta is what I get by foiling this. D theta. For the trick for integrating cosine squared, there's other tricks too. There's reduction formulas and so forth, but it's a nice way to integrate cosine squared. Now here's a half angle. Rewrite that as 1 plus cosine 2 theta over 2. So this is now the 1/2 the integral from minus pi over 3 to pi over 3. And I've got 1 here. Plus 4 times a half here is 3. I guess I put it on. Let's just write out steps. 1 minus 4 cosine theta. Sometimes I try to do too many at once. Plus 4 times this is 2 plus 2 cosine 2 theta. This one has the area of the inner loop. Let's call it 1/2. Now integrate this 1 plus 2 is 3 theta. That's 3 2 theta. Integral of minus 4 cosine theta is minus 4 sine theta. Integral of 2 cosine 2 theta is sine 2 theta. And I need to plug in minus pi over 3 and pi over 3. Well, if you're clever, you can recognize that by symmetry, this is actually twice the integral from 0 to pi over 3. That would save, and you can get rid of the 1/2. That would save you a little trouble here, but let's assume we don't notice that. Symmetry will save you a little work there. But now we can say this is 1/2. Plug in pi over 3 times 3 theta is pi. Minus 4 sine pi over 3. Plus sine 2 pi over 3. And we subtract that from that. Putting in minus pi over 3 minus pi. And minus 4 sine minus pi over 3. And plus sine minus 2 pi over 3. These double each of the quantities. What we really wind up with then is pi minus 4 sine pi over 3 plus sine 2 pi over 3. This one is minus this one, so when you subtract it, you get 2 of this one, and then that gets rid of the one. All right, so this is pi minus 4 times, what's the sine of pi over 3? Again, you go back, you can look at the special triangle, pi over 3, a 60-degree angle, and say, oh, the sine is square root of 3 over 2 on that, right? Opposite over hypotenuse. Sine of 2 pi over 3, you can remember the circle. 2 pi over 3, you get the same triangle over here. And again, sine of 2 pi over 3, 30, 60, 90 triangle is square root of 3 over 2. So we get pi minus 3 square root of 3 over 2. Here's the area. So phone problems you do like that, and they make you think a little bit about polar coordinates too. Any questions on this one, anybody? Haven't heard anything from people online yet, so. I was worried I don't have the camera on or something. If you talk to me, then I know you're there. Let's see this up. I would hate at the end of the semester to find out nobody was there. Talk to the wall. So here's one more, the last one. We talked about roses, right? Find the area, one petal of the rose R equals 3 cosine 2 theta. It's useful to remember what these figures look like. Remember what happened if you had a cosine n theta or a sine n theta. It was rows of petal length A. And if n was odd, then you got n petals. But if n was even, then you got 2 n petals. In case n was odd, you went over each petal twice. This theta went from 0 to 2 pi. So you only got n petals. But if n was even, then you had 2 n petals. So this is actually going to be with n even, you got a 2 n petal rows. And with n odd, you got an n petal rows. So evidently this has 4 petals. Each petal length 3. So that gives me a hint at sketching it. How do I find where a petal begins and ends? Well, you might say, well, what makes R maximum? The maximum radius is when cosines equal to 1. So, it works when theta equals 0 for 1. Max R for theta equals 0, then I get R equals 3 cosine 0. It's 3. So that's the maximum petal length. That's right in the middle of a petal. Now, on each side of that, what's the first time that R is equal to 0? When R equals 0, that's when a petal begins and ends, right? It's when it goes through the pole. So what's the smallest positive angle that will make cosine 2 theta equals 0? Well, on cosine equals 0, the first time that occurs after 0 is when the angle is pi over 2, right? You're looking at the unit circle. Cosine is equal to 0 and pi over 2. That's the first time for a positive angle. So it must be that we want 2 theta equals pi over 2. Now, so for R equals 0, we have theta, 2 theta, the argument of cosine, equal pi over 2. Pi over 2 is the first positive angle for which the cosine is 0. We want 2 theta equal pi over 2. And also the first negative angle. I go back this way. The first time I get a negative angle giving cosine pi over 0 is at minus pi over 2, right? This angle. Because cosine is the x coordinate. So if I want 2 theta equal pi over 2, divide by 2. 2 theta equal minus pi over 2 this time. Which means that theta equals pi over 4 when it ends, and theta equals minus pi over 4 when it begins. Now we know how it works. 4 petal rows looks like this. Really helps to sketch. It has a petal like this. Length 3. Starts at an angle. Theta equals minus pi over 4. Ends at an angle. Theta equals plus pi over 4. You can imagine how it goes now. Theta equals 0, but as you run along this portion of the petal, here's theta equals 0, you get 3. Theta equals this angle, you get this distance. Theta equals this angle, you get this. Theta equals pi over 4, you get back to 0. Now you get negative. As you turn up here, R gets negative, and you sweep out a petal over here of length 3, and a petal over here of length 3 with positive R, and then a petal over here of length 3 with negative R, and that's what the rose is going to look like. It's just like that. Let's look at the area of this petal right here. Right? We just have to go from theta equals minus pi over 4 to theta equals plus pi over 4 and apply this formula. So we'll say area is equal to 1/2 the integral from minus pi over 4 to plus pi over 4. R of theta squared, where R this time is 3 cosine 2 theta. d theta. There it is, our formula there for this function with the correct angles. Once again, we can do the trick. We'll pull the 3 out, or the 3 squared out. That becomes 9/2. Integral from minus pi over 4 to plus pi over 4. Cosine squared 2 theta. D theta, we can pull the same trick as before. This is 9/2 integral from minus pi over 4 to pi over 4. 1 plus cosine 4 theta over 2 using the half angle identity. And now we can integrate it, right? Because integral 1/2 is 1/2 theta. Integral of cosine 4 theta is sine 4 theta, and then that's divided by 2. So I get plus 1/8 sine 4 theta. Plug in minus pi over 4 plus pi over 4. And nicely then sine 4 theta, sine of 4 times 4. I have 4 times pi over 4, sine pi is 0. And sine of 4 times minus pi over 4, sine of minus pi is 0. So this one's actually not going to contribute anything. We can just drop it out, right? These two angles, it's going to be 0. All we have is 9/2 times 1/2 pi over 4 minus 1/2 negative pi over 4. Well, a half pi over 4 plus a half pi over 4 is pi over 4. We get 9 pi over 8. There's the area. All right, well, with that, I'll close the section then. And the next section will be a really fun one, I think. Of course, something you might have seen before in trigonometry, depending on how much time your class had. We're going to do the calculus of it, though. Conic sections, calculus with them. These are extremely important because they come up in lots of interesting applications. And you can see why when you think about it a little bit. But there are 4 conic sections and then some degenerate cases. However, one way to generate conic sections is like the ancient Greeks did. The ancient Greeks used to do all their geometry with just a compass and straight edge. So they would do proofs with the compass and straight edge. In Euclid's Elements, for instance, the 7-volume work on Euclidean geometry, they did that. But what it becomes natural then when you extend this to 3 dimensions, say, well, suppose I have a point, another point, 2 points determine a line, right? That was one of Euclid's postulates. Now suppose I do the natural thing for people who like points and circles, and I hold this point fixed, and I rotate this point in a circle. Then the line rotates around like that, and I generate, the line goes on forever, what we call a cone, by holding one point fixed and rotating the other one in a circle. Now you think, what else could I do? I could take 2 points and I could slide them both parallel to each other. I take the line through the 2 points and I slide both points, the whole line, forward, then I get a plane, right? Now what happens if I intersect this plane? I got by sliding the 2 points of the line, and the cone I got by holding 1 point fixed and rotating in a circle. This intersects actually in a circle. Right, because every point along the line moves in a circle when you rotate it. So that's one conic section because we cut a cone. We call it a conic section. But there are others, right? Suppose I, instead of putting the plane just like that and sliding it horizontally, suppose I slide it at a little bit of an angle. That. Just a small angle. Then what happens? it doesn't cut it in a circle anymore. It cuts it in this kind of an oval shape that we actually call an ellipse. Now I could cut it a little steeper. Maybe I could cut it as steep as this line segment here, right? If I cut it parallel to that line segment like this. I wonder what shape I get now. Right now you're playing with something like this. Well, it doesn't intersect on both sides because it never comes over here to cut this line, but it intersects in this open curve that we call a parabola. Then I can take this thing and turn it even steeper than parallel to the side. Maybe I cut it like this. I think the book shows it perpendicular, if I remember right. Suppose I take this kind of a plane and cut it. Now what do I get? I intersect it in this kind of curve here. And furthermore, I intersect the bottom half of the cone, if I keep going here, and another piece down here. Turns out they're in the same shape, and each one is called a branch of a hyperbola. So depending on the angle at which you cut the cone, you can get a circle, an ellipse, a parabola, or a hyperbola. Let's see if I can share the screen on here. Hope this is going to work. The line, can you see the parabola, the conic sections there? Volume's turned way down. I believe it says you can now see this. Doesn't. You see the cone online? I don't see it on the screen there, but I think you can see it. Anyway, so it shows those four shapes is the idea. Now, what's more is you can, there's a nice history to these. I just took this from the Wikipedia article. All you have to do is Google Wikipedia conic section to get this same thing come up. This shows the cones here, the cone being cut here. Here's some ancient drawings of cones. But they come up in all sorts of situations. Here's another case where they come up, is in orbital mechanics. I can see it in here. Let's see if I can get it. See it on the screen. Okay, yeah, it's not easy to see. Well, you can go to Wikipedia and look this up, and it shows, maybe I'll draw it on the board. Yeah. If you put the sun at that one point, you can put a circle around it. That's a perfect orbit that can be done. But if you give something a little more, take something that's going in a circle and kick it a little bit, it can go into an elliptical orbit. You see the ellipse there, and if you give it just enough velocity to escape, like you have an asteroid that comes from the farthest reaches of space and just grazes by the Earth and just escapes to infinity, that executes a parabolic trajectory. If you have something that has more than escape velocity, then you get a hyperbolic trajectory. So those are the conic sections in orbital mechanics. And there's lots of other cases where these come up. This is a very fun one here. This is the ellipse. There it is. Maybe I'll just do these in the board. I'm not sure if anybody's seeing this or not, so I'm going to stop sharing the screen in case. And we'll draw some more on the board. So applications, for instance, include orbits. If you put the sun here, you can have an object go around in a perfect circle. That works with the sun at the center. But you can also make an ellipse where it turns out the sun isn't one focus. There's two foci, and we'll talk about an ellipse, what the foci are shortly. Or you can do a parabolic trajectory where it just has escape velocity, or you can do a hyperbolic trajectory. The hyperbola has asymptotes. The two directions get closer and closer to lines like that. So there's the conic sections in action. And then other applications, I brought some of them. We might do a couple more next time. Hopefully you can see this. Here's my bouncing ball. All right, I've got carpet in here, so this bounces real well. But where's the conic section in that? You can see the ball is circular cross sections. Well, what's it doing there? On each bounce, ignoring air friction, you can show by Newton's laws, and we can actually show that in this class, that the ball actually executes a parabola. If you assume constant gravity vertical, then that shows that the ball goes in an exact parabola. Now it ignores air friction, it ignores that actually gravity is quite constant because you get a little further from the center of the Earth, there's a little difference. But to any reasonable, to huge approximation, the ball goes in a perfect parabola. So bouncing ball going through the air, each bounce is a parabola. Bouncing in constant vertical gravity executes a perfect parabola. And there's more applications. If you've ever seen those charged particle things where they have a charged particle and another one goes by like that. They shoot it by and it arcs like that. Well, it executes a hyperbolic trajectory because it has the same kind of force law that planetary do. So the force is inversely proportional to the square distance between the two, same as gravity. So in these bubble chambers where they make the little tracks of charged particles, they get hyperbolic trajectories. Those. Maybe somebody's seen a whispering gallery. Ever seen one of those where you sit in this kind of oval shaped room and two people sit right here very, very softly. And someone standing right in the middle can't tell what they're saying. They're speaking so softly, but they can hear each other. Why is it they can hear each other? It's because the room is the shape of an ellipse. And an ellipse has this property that if you speak softly here, all the sound bounces off the wall and goes straight over the other person. Using angle of incidence equals angle at which it exits, always forces every bit of sound this point to this point. Same thing with light, using angle of incidence equals angle of reflection. All the sound is reflected to here, so this person speaks very softly, and except for what's lost by the wall's vibration, it all just comes back here to this one. And this person can hear even though the one in the middle can't, because they don't get all the sound coming to them like the one at the other end does. So that's a whispering gallery. I've also seen it done. Here's an application of parabolas again. I've seen it done at the Kirkpatrick Center right here in town, where they'll put a parabola here and a parabola here. And one person sits here and one person sits here. Now what happens is all the sound comes off this and bounces off a parabola. The property of the parabola is it takes all sound from a point or all light from a point, reflects it using angle of incidence equals angle of reflection into straight lines. So all the sound coming off bounces into straight lines like that. It then bounces off this parabola, which refocuses it in straight lines. And this person can hear tiny whispers. It's really neat. Go down there. I hope it's still there. I saw it there years ago. And this person can hear what this person's saying very clearly, but somebody is standing anywhere else can't, because the two parabolas between them refocus the sound. Yeah, the Science Museum at the Kirkpatrick Center.
Oh, that's what you're saying.
That's what I'm talking about, yeah. Yeah. And then I have a whole thing in my office. I didn't bring it tonight. In a class where we can handle things, I pass it around. My dad knew the guy who invented this, actually. But it's this kind of a thing. It's a dish like this, a dish, and then another dish just like it on top, except it has a hole cut in it. And so I don't know if you can see this or not, but the idea is it's a mirrored dish down here and a mirrored dish up here with a hole in it. And what happens is you place a coin down at the bottom, a quarter or something, and light coming off the quarter, because this is a parabolic surface, it's a parabola of revolution. The light coming off here is focused, and this is the focal point. It bounces into straight rays. Well, then it bounces off the straight rays here and refocuses each point of light up here. And so the light coming off here is refocused here, the light off at this point is refocused right here, and so forth. It makes a perfect image of your quarter up at the top. And it looks like it's sitting there. You try and grab it, but it's not there. It's a hallucination. You ever saw, what's the name of that movie? Can't remember. There's a movie where they had a projected figure and he's running along, and Arnold Schwarzenegger was in it. They made a remix since then. They shoot him, but they don't ever hit him because they're looking at his reflection. Yeah, that's how you can make these fake images. Then a hyperbola has this optical property. If you take the hyperbolas, if you put something at the focus of a hyperbola, say, and you let's see. Something at this focus here, the light bounces back. Over here, it bounces out like that. Over here, it bounces out like that. An object here at the one focus of the hyperbola, forget this branch, allow it to bounce off this mirrored surface here, reflects as though the light was actually coming from this point. So you can put something here and make it look like it's sitting there, but actually you're just looking at the mirror here. All this is bouncing off. The light bouncing off just bounces off, but as though it came from here, right? And so you can do that with hyperbolas. If you've seen some of these fancy telescopes, I have a telescope in my office. It's called the Newtonian telescope. Isaac Newton made this. They had problems with telescopes. They used glass in them, and the glass would bend different colors of light a little different, so you get this so-called chromatic aberration where the reds and the blues got smeared when you looked through them. He came up with this great idea that you put a parabolic mirror at the bottom of your telescope dish, at the bottom of your telescope, a parabola of revolution, so you actually make a dish out of it. And the light coming from infinity is now, by the properties of parabolas, is refocused to a point up here. But before it's refocused, you intercept it with a flat mirror like that. And it bounces it off so it reflects over here. Then if you put an eyepiece over here, you can put a lens in here and focus on this little image that's created. Maybe there's a star out here that you're looking at. If it's far away, it takes the parallel light rays, bounces it to a point. And when you look at it through the little image, it blows up the image in a ratio of the focal distance of the big one to the focal distance of the small one. So if this distance is 100 times this distance, then the thing looks 100 times bigger, it turns out. We won't get into the mechanics of that. But the point is, you use a parabola here to make a telescope, and now you're done with that chromatic aberration. There's no lenses down here. There's just this little lens here, which doesn't affect it so much. And Newton was able to come up with this telescope that then got rid of chromatic aberration pretty much. And it works pretty well. I put one together like that when I was in college years ago. And so here's a telescope tube, and you put this parabolic mirror. However, they found out that you can make telescopes shorter. These tend to be pretty long telescopes by doing the following. You got your telescope pointed out at a star. You can make it shorter, and you can actually make this big primary mirror easier. It's hard to make it a perfect parabola. What's easier is to make a piece of a sphere down here. If you make a piece of a sphere down here, then light isn't reflected to a point. It's kind of reflected towards a point. Well, what happens is they put a hyperbolic mirror in here. And if you put the hyperbolic mirror in here, then between the sphere and the hyperbola, you can make all the light focus to a point. And then you put your lens back here and refocus. And again, the effective focal distance of moving at this last angle, so the focal distance of the little lens increases your power. But between the circle of revolution and the hyperbola of revolution here, you can create the effect of the parabola, focusing straight line beams to a point, and make a telescope that way. And now it's much shorter because it bounces between these two, and this one kind of spreads the angle out. You make a high-power telescope that's not so long. So there's lots and lots of optical things that happen like that. There's a game called Elliptopool, maybe you've seen. It's got a pocket at one focus of the ellipse, and then it's got a spot on the table. If you shoot the ball over the spot without spin, so it uses angle of incidence equals angle of reflection, it always goes in the pocket. All you have to do to put it in is run it over this focus. Now, if you spin it, then it won't bounce off the wall, right? But, so elliptopool works that way. There was an elliptical wing on one of those World War II fighters, and they used that, its properties. So these things come up in lots and lots of applications. Flashlights, you ever seen how a flashlight works, right? You have a mirror down here that ideally is a parabola. Don't try and make them real accurate for flashlights, they're too cheap. But if you put the light bulb at the focus of the parabola, what happens is you get a big circle on yonder wall here. I put a projector screen here. That comes from the light coming out through the circle here and making a big diffuse circle of light on your wall. But the light that goes backwards and strikes the mirrored surface, if it's a parabola, it all focuses out in a beam and makes a small bright circle here. That's from the parabolic surface. And so the beam part is actually from the parabola. Those radio telescopes, right? Those are parabolic things that refocus radio signals coming from far away to a point and get a strong signal that way. That's how all that stuff works. So these are used extensively in all sorts of applications. Maybe those too long to go on, but thought I'd show you a lot of neat things that make these kind of fun. And now, how can we analyze these better than saying they're cross sections of a cone? And I should mention a couple other things too. There's also degenerate cases. There's 4 conic sections: the ellipse, the circle, the parabola, and the hyperbola. And then there's degenerate cases. You can get a point, right? You can intersect the cone right through the middle there and make just a point of intersection. You can make a line by intersecting it down along the edge, right? Here's the cone. So you can run it right through here and get a point. Or you can run it right down the edge and just get this line. Or you can run it right down like this and get a pair of intersecting lines. All right, so these are not degenerate cases. Which are useful, but we already know all about lines, right? So we don't worry about those so much. How can we get equations for these things? Let's look at them one at a time. The circle is an easy one. You've already done that pretty much. How can we get the equation for a circle? I'll say another way to define these things is to say a circle is the locus or set of all points at a given fixed distance r greater than 0. Called the radius from a given point x naught, y naught, called the center. The center and a radius define the circle. And here's the center, and then the circle is these points out here, not the center itself, right? And all the points at a distance r. Well, how can we get the general equation for a circle? You've seen this before, but I just want to remind you quickly, make sure we're all on track here, especially because it relates to the next topic we're going to talk about. Well, by the distance formula, this is all points x, y, such that the distance between x, y Here's a point x, y on the circle, arbitrary point. Here's the center, x naught, y naught. Such that the distance between these two is r, right? X minus x naught squared plus y minus y naught squared equals r. That's the criterion for the circle. Now you square both sides and get equivalently x minus x naught squared plus y minus y naught squared equals r squared. Here's the standard equation for a circle. Whenever you see that, it's a circle of radius r with center x0, y0. So that's all with that one. We should do an example. The equation x minus 1 squared plus y plus 3 squared equals 4 is a circle at center 1 minus 3, what's subtracted from these coordinates, of radius square root of this number, right? That's r squared on the right. There's an example circle. Number 2 is the ellipse. Once you've seen the circle, this is a nice generalization. An ellipse, this is the locus of all points x, y, such that the distance from x, y to 2 given points this time. The distances from x, y to 2 points, distinct points, is a given, summed is a given number. We can illustrate this real easily. Actually, this will have such a nice construction. Here's how I can generate a near perfect ellipse. I got 2 suction cups and a string of fixed length, right? So what I do is I take these two. These will be the 2 foci. I should mark these things. The 2 given points are called focus, or each called focuses. And so this is a plural focus is foci. And then there's some distance. I think it's 2a, is a given number 2a. And what you do then is you want the sum of the 2 distances. Well, say the length of the string is the sum of the 2 distances. And if I just hold my marker here, here's all the points. That's the sum of the 2 distances from the 2 suction cups. The constant, and there's what the ellipse looks like. It has these foci, and the length of this string as 2a. So it's an oval shape. And as those foci come together, it degenerates into a circle. So a circle is the degenerate case. Now, what could be the equation of an ellipse? If we do this, this will be the standard equation for an ellipse, and then we'll translate it to be at any point later. What we like to do is put the origin halfway between the foci and say this point has coordinates minus c0, and this point has coordinates c0 with the same c for some c, some c greater than 0. Generates the ellipse where all these distance 1 plus distance 2 is equal to the common fixed number 2a, no matter where you are. This distance from this distance plus this distance is also 2a, and so forth. All right. Now, what does that say? This requirement is the distance formula again. if I call this point an arbitrary point on here, x, y, well, what's the distance to this point? X minus c absolute value is this, x plus c is the absolute value of this one. X minus c is this one. So we'll say the distance to this one is x minus c here, and this one is y, because it's going from 0. So x minus c squared plus y squared square root is d2. And then d1 is x plus c squared plus y squared. And that all has to add up to 2a. Now what we can do is from algebra, we try and solve this, and we say, well, it's square root x minus c squared plus y squared equals 2a minus square root x plus c squared plus y squared. And you square both sides, and you get x minus c squared plus y squared equals 4a squared minus 4a times the square root out of algebra plus this squared is x minus c squared plus y squared. Oh. So that's squaring both sides. And now let's see, we've got an x plus c squared on each side, so we can cancel those out. We've got a y squared on each side. Oops, no, it's not. This one's x plus c. I'm sorry, these don't go away. X plus c squared. Canceling the wrong stuff. I can cancel some of it, it turns out. I can cancel the y squared on each side. Furthermore, this is x squared minus 2cx plus c squared, and this is x squared plus 2cx plus c squared. And so I can cancel the c squareds and I can cancel the x squareds. And now I've got minus 2cx this side equals, actually I can have the, let's subtract the minus 2cx over here. I better write this. Minus 2cx equals 4a squared minus 4a times the square root plus 2cx. I get that. All right. Now I'll subtract everything but the square root over here and square again. So now I've got minus 4cx by subtracting that other one over. Minus 4a squared equals minus 4a square root x plus c squared plus y squared. Right. And now we can divide by 4a, by minus 4a, and get cx plus a, dividing by minus 4a, equals square root x plus c x plus c squared plus y squared. So I square again, and I get c squared x squared plus 2acx plus a squared equals x plus c squared plus y squared. So all these are equivalent. Has to be careful squaring both sides, but now what have we got? Let's see. This comes out to be x squared plus 2cx plus c squared plus y squared equals all this. Equals c squared x squared plus 2acx plus a squared. And you can subtract the x squared over and write this as c squared minus 1 x squared plus 2acx minus 2cx over here. Did I miss an a? Oh, wait a minute, I didn't subtract right. This isn't it. I thought that looked wrong. I was supposed to just divide by minus 4, not by minus 4a. Oh, got that messed up with that one. I'm gonna have to come back here. I divide, and so this is minus cx, and this is a squared, and this is a here. Now I square this one, and I get c squared x squared plus 2 ca squared x plus a to the 4th equals a squared times all this stuff, x plus c squared y squared. When you mess around with this just a little bit, I'm going to leave out the rest of the algebra. You can work this down where it actually says x squared over a squared plus y squared over b squared equals, I'll say I'm leaving out the algebra here in order to make it not take too long. But you work it out like that where b is what? B is gotten by saying a squared equals b squared plus c squared. In other words, b is the square root of a squared minus c squared. So you define b to be this number, and then you can rework this into this form eventually. I don't take it too long, so we can abbreviate that a bit. And that is the equation for the ellipse with foci at plus or minus c, and sum of distance is 2a. So that is, this is the ellipse in standard position, x squared over a squared plus y squared over b squared equals 1. Is with a squared equals b squared plus c squared, we're relating these three numbers a, b, and c, generates an ellipse. But you get it by doing the same thing, writing the distance formula and squaring and doing a lot of algebra. All right. That's the equation. Now we got to try and sketch one of these. Suppose I said sketch the ellipse x squared over 9 plus y squared over 4 equals 1. I wonder what that looks like. Well, if you think about it, the ellipse shown A and B have very important geometric characteristics, right? We said the foci were at plus and minus c, so here's minus c0 and here's plus c0 when we generated this. But furthermore, 2a is the length of the string. So if I go from here down to here and back to here, that must be 2a, right? Because it's down and back, down to this point and back, right? It's property of the ellipse. But this distance is also this distance by symmetry. So 2a is also this length. we say that the major axis length is 2a. So here, a equals the semi-major axis length, half the length of this major axis. That's how you sketch it. Well, that being the case, this point here must be a0, and this point here must be minus a0. So when you write an equation for an ellipse, you know immediately 2 points on here are the square root of this, 0, and minus the square root of this, 0. 0, 3, and 3, 0. I can write those immediately. Let's sketch my ellipse. Since this is 3 squared, I know there's a point of 3, 0, and a point, same distance the other side, at minus 3, 0. Now, what about the other one? Well, you notice that if you put x equals 0, you can also get this by putting y equals 0. Then you get x equals plus or minus 3 in order to make this equal to 1. You can also get the points that way, but I wanted to relate it to the 2a in the formula. Now, if you put x equals 0, then you get this term falls out, and you get y squared over 4 equals 1. Y has to be plus or minus 2. Same thing here in the general form. If you put x equals 0, you get y squared over b squared equals 1, says that y has to be plus or minus b. So the points here are always 0b and 0 minus b from the equation. And we call b the semi-minor axis length. It's the shorter length. So this one has semi-major axis length 3 and semi-minor axis length, since this is 2 squared, 2. So I'll go up to the point here, 0, 2, and down to this point, same distance the other side, 0 minus 2. We run the ellipse around like that. There it is. You just got kind of an oval shape. Or if you have 2 suction cups, you can draw it more accurately. So there is a nice sketch of an ellipse. Now, suppose I said find the foci. Sketch and find the foci. How do I find the foci? From the equation, right? Well, the foci come out of here. When you do that derivation, you can actually get y squared over a squared minus c squared. And then you call that b squared. You just define b that way. So, but that tells you how to find b. Or you can find c this way. C, evidently, from this equation is the square root a squared minus c squared, b squared. So since we know a and b from the equation, it's square root 9 minus 4 is square root 5. Apparently, the foci are at square root 5, 0, and minus square root 5, 0. Now I've got my ellipse nicely drawn with the foci. Now, what if you want a more general ellipse? Find the equation of the ellipse with foci 2, 7, 2, 1. Now there's something strange. The foci are vertical instead of horizontal. So we need to note that if you want vertical foci, then you have to rewrite the equation. How can I rewrite the equation? Well, I just need to rewrite it this way. This is for semi-major axis along the x-axis. Oops, I'm sorry. This should be not jumping ahead my example here. Let's make it at 0, 3, and 0 minus 3. Sorry. Vertical foci have with center at the origin is x squared over b squared plus y squared over a squared. A being the bigger number in this diagram here, A bigger than B is supposed to be the bigger, the semi-major axis. If you put A equals B, you actually get the circle equation, see, right? So here's the vertical one with center at the origin. You just interchange A and B so that now Y sits over the bigger number. And so we can find this one. What is the focal distance? C is half the distance between the foci is 3. Half distance between foci. And now, oh, and I need one more thing here. And semi-major axis length 5. Yeah, semi-major axis length 5. Well, semi-major axis length 5 is A. So I have C equals 3, and I'm given A equals 5, so B is the square root of 5 squared minus 3 squared, turns out to be 4. So I have B equals 4. Now I immediately know the equation. Therefore, for vertical foci, I use this with this A and this B, right? And I just have x squared over 4 squared plus, 3 squared. 4 squared plus y squared over 5 squared equals 1. There's my. And then you might ask, what if it's not centered at the origin? There's an easy way to translate this, just like you translate any curve. If I wanted to center it at some other point, just place x by x minus number and y by y minus number. You can translate this. We'll do this next time. I do have one thing I want to make sure I do before we go. Here's how you can generate a nice hyperbola. This is a stretchy string and 2 peanut butter can lids. If you twist this is another thing they have at the Science Museum. You can get a hyperbola revolution. They call it a hyperboloid. You'll see those later. But there's how hyperbola occur naturally. This is called a lineal surface because you can see from the stretchy strings, it's actually generated by lines. So if the whole surface can be generated by straight lines like these stretchy strings, it's a lineal surface. And this is a hyperbola. Hyperbola revolution is a lineal surface. Anyway, so these things come up in all sorts of applications. We'll continue. Maybe I should give the homework out on this. I don't tell you what. Finish the homework we did on the polar coordinates for this time, because I'm really not far enough to give all the first couple problems on ellipses here. We'll finish these. I'll give you a whole bunch of problems next time. Thank you, everybody.